The maximum flow problem asks, how do you route the absolute maximum capacity of material from a source through a network to a final sink? This animation shows the standard approach, like the Ford-Fulkerson method. It solves the problem by searching the entire network to map out valid, continuous paths from start to finish. The bottleneck in mapping the whole route is overhead. The algorithm must constantly query the state of distant nodes to calculate a single valid path. The Push-Relabel algorithm drops this requirement completely. It abandons global pathfinding. Instead of mapping routes, the network is immediately flooded. Intermediate nodes act independently, completely blind to the overall graph structure. We can solve a massive global network problem by forcing individual nodes to blindly follow strict, isolated rules. Every node in this system tracks exactly two local variables. The first is excess, the amount of incoming flow that exceeds outgoing flow. The second is height, an artificial distance metric used to guide that flow towards the sink. We can visualize this state physically. Look at this single node, represented as a container. The physical elevation of the cylinder on the y-axis represents the node's height, while the volume of liquid inside measures its excess. The algorithm relies on one absolute physical rule. Flow only pushes downhill. A node can only transfer its excess liquid to a neighbor sitting at a lower height. By tracking nothing more than the fluid level inside them and the elevation of their immediate neighbors, these nodes organically route traffic through the network. This diagram shows our starting network. The source, the sink, and all intermediate nodes sit at a baseline elevation of 0. Empty pipes connect them, each labeled with a fixed capacity limit. The algorithm begins by artificially elevating the source node. Its height is set exactly equal to the total number of nodes in the network. Then we saturate all outgoing pipes from the source to their absolute maximum capacity. Here, liquid floods from the source into node A, filling it with 15 units of flow. Node A now holds a localized state. It has an excess of 15 and a height of 0. With a full container, node A must attempt to push its excess to its neighbor, node B. But the flow cannot move. Both node A and node B are currently resting at height 0. This deliberate initialization creates an immediate bottleneck, forcing the algorithm to rapidly react and start shaping the entire network. A bottleneck occurs whenever a node holds excess flow, but has no neighbors at a lower height to receive it. The algorithm resolves this with its second primary action, the relabel operation. Relabeling follows a strict mathematical rule. A stuck node updates its height to exactly one step above the minimum height of its lowest valid neighbor. Look at node A and B. Node B's height is 0. Node A looks at that 0, adds 1, and calculates its new height. Node A elevates to height 1. This +1 constraint is vital. It prevents nodes from jumping to extreme, unhelpful heights, ensuring the gradient is only ever exactly as steep as necessary to resume flow. Relabeling acts as an artificial gravity generator. It dynamically constructs downhill slopes exactly where the fluid gets trapped. Now that node A sits physically higher than node B, the push operation is unlocked. The amount of liquid pushed forward is strictly determined by the minimum value between the node's current excess and the connecting pipe's capacity. Node A has 15 units of excess, but the pipe connecting it to node B can only handle 12. The algorithm calculates the minimum, 12 units, and pushes that exact volume downhill. Node A retains 3 units of undeliverable excess, and node B takes on 12 units of excess. The push successfully cleared a portion of the immediate blockage at A, but it simply shifted the localized pressure down the chain to B. To handle flow that eventually hits a dead end, we have to look at what happens behind the moving fluid, the residual edge. Whenever liquid moves forward, a residual path forms pointing backward, carrying a capacity exactly equal to the volume just pushed. If we let the algorithm run, node B will push its flow forward to node C and eventually the sink, but it might hit a dead end where all forward pipes are completely full. Let's look at the scenario where node B is left holding an excess of 2, with nowhere left to push forward. Node B follows the rule. It repeatedly relabels, driving its own height up until it sits physically higher than the node behind it. The gravity gradient is now reversed. Node B pushes its 2 excess units backward through the residual edge, returning them back to node A. If node A also finds no forward path, it will undergo the same relabeling process, spiking its height to 8, reversing the flow all the way back to the original source. These residual edges act as critical pressure relief valves. They guarantee that any fluid physically unable to reach the sink is reliably rejected and returned to the source. How does an algorithm built entirely on the isolated state of single nodes know when the entire system is finished? It relies on one strict termination condition. It halts only when every single intermediate node has an excess of exactly 0. Looking at the network at once, the process looks like chaos. Nodes constantly bounce up and down, frantically passing fluid forward and backward as they adjust their local heights. But this continuous loop is mathematically guaranteed to converge. The movement locks in, the container's empty. The network achieves a perfect, globally optimal flow distribution, generated entirely by the sheer collision of simple local adjustments. The maximum flow problem asks us to find the absolute limit a network can carry. To solve it here, we never calculated a single continuous path from the start to the finish. We distilled the entire complex process down to just 2 simple elementary rules: push downhill and relabel when stuck. Because these operations only require local data, the algorithm is highly efficient. It can be easily divided and processed in parallel across modern computer architectures. True optimization doesn't always require seeing the whole map. Sometimes you only need to measure the height of the step directly in front of you.